Okay, so next speaker is Zhang from MRC LMB, and he's going to talk about GCTF and I guess programs. He's written various programs that a lot of us use, so some of this will be very familiar to some people.
Yeah. Thanks, Helen, and thanks for invitation. So today I'm going to talk some recent development of GCTF. There's nothing faster. It's basically diagnosis, accuracy, and localization. All my talk will be based on these three major topics. So first of all, let's have a brief look about what is the contrast transfer function. Here is a 3D density map. You do a projection, and you get a nice linear integration of the 3D density function. But actually, unfortunately, what we observed in the CCP-EM micrograph is usually something like this. It's severely convoluted with a point spread function and highly modulated by this function called CTF. And in real space, it's a convolution. And usually we interpret it in reciprocal space and under strict weak phase approximation. And it's a simple multiplication. That's the reason why you already understand it in fair space rather than real space. But in practice, things is much more complicated. I mean, the object is not usually, not usually obeys strict weak phase approximation. You have noise from the sample itself and noise from the TEM image formation, and also in the final step about the detection. And also it's a 3D object rather than a 2D object. And let's have a look how the CTF modulates your structure information. So typically, CTF is a sine-like function. And two most important factors is spheric aberration coefficient and also defocus. But in the case of the phase plate data, we also have another unknown parameter, the phase shift. And here is a simulation about typical CDF curves. And in 2D, it looks like this. And in GCTF, the target is basically trying to estimate the unknown parameters that we lost during the experiment, because for other factors like the CS or the wavelengths, we all know about these parameters, but not the defocus or phase shift. That can't be accurately controlled during the experiment. So that's the target in GCTF. So basically, you get rid of the background and maximize the cross correlation between the simulated CTF and the observed power spectrum by maximizing this function and get the best estimation of these unknown parameters. And GCTF uses a strategy called one-dimensional search plus two-dimensional refinement. And with phase shift, you need higher dimensional search, of course, and modified simplex algorithm for refinement and GPU acceleration and optimized programming strategy. But I'm not going to talk anything about the speed. I'm more interested in the accuracy and validation, diagnosis, things like this. So how does CTF perform, or what about the accuracy of CTF? So usually we can easily verify the performance of the program by some method called the self-consistent verification. That means you use different parameters or by running it by multiple times. But I would suggest experimental validation should be the ideal approach to validate the program. So how does it work? So we collected a set of the defocus series. Just simply by adjust the focus button, and then we estimate the CTF for this focus series, and then because the starting focus is usually not accurate or can't be precisely controlled, we use the difference of the defocus rather than the absolute defocus to estimate. And then you plot the difference between the experimental values and the calculated. And what I found interesting that you can see when you increase the defocus, the error becomes bigger and bigger. And I was curious what happened and tried the whole range of defocus and found the same phenomenon. It's always the same, and when you increase the defocus and the error becomes bigger. So it doesn't make sense because when you increase it, the error becomes bigger. But at the same time, when your starting defocus increase, the error always starts from very small. And that means there must be some systematic error during the experiment. That's the reason why we need to correct the experimental values just read out from the microscope. That means it's not precisely correct of the defocus we read from the microscope using the focus button. And then we fitted a linear, and we correct the experiment defocus by applying a linear function to fit the estimated defocus values, and then use the corrected experimental values, and then we can estimate the errors. And this is the final error. And got about the accuracy of the GCTF, like 14 angstroms. This is on carbon. I had some problems on ice. That's because of the high beam-induced movement and charging and burn of the samples. You can't do, constant exposure on ice. That's some problem during the experiment. But anyway, so as probably many people who already tried GCTF knows that it performs a good job in general case. It might fail, occasionally, but for general computation should be fine. I'm going to talk more about some challenging case like the phase shift estimation. Although a phase shift, it seems that it's only one parameter more, but you think about the parameter space, it's much bigger. It's almost hundreds of times bigger than the original parameter space. So previously, I used a slightly modified approach, just like the normal micrograph, and searching both the phase shift and the average defocus in 1D. But initially, I found that this approach actually doesn't work well in many cases. And then I improved the approach slightly by searching the phase shift, and at the same time, searching the defocus in 1D, refine it in 2D, and then refine all the parameters again. But these two approaches usually works much better than the faster 1D search. For phase plates, for normal micrograph, they work almost the same. But for phase plates, 2D search is still better. And this is some feedback from the phase plate users. And I'm not claiming that GCTF is doing better in all cases. This might be just a special case that people found improvement of GCTF and found the result is better. So if you find in some case GCTF, get some worse results, please also report it to me. And I'm interested to test what was wrong or could potentially improve. Because if I need some data or some special case to see how we can improve. I don't just need the positive feedback. And in fact plate, sometimes things is very challenging because for some reason the high frequency signal seems to be lower compared to the normal micrograph. And I got a data set from Professor Yun Xiong from Yale University and try to estimate the phase shift. And it seems that there is a very big error. And then what I suggest is trying to smooth the phase shift by fitting like the polynomial and by least square method, and then use the smoothed phase shift to refine it again. And then you can see before the smoothing and after, and the phase shift it seems much better. But I should also warn people that this might be dangerous because you can, if the constraint is too tight, you might overfit the bias. In the ideal case, why not use a completely smooth curve to apply that value as your phase shift? That seems, seems it's reasonable, but actually the smooth curve itself can be severely biased. So we don't want that. We just use that as a constraint to constrain the refinement rather than use that as estimation. In addition to the statistic verification of your CTF estimation, I would suggest that we use some direct visual validation because we can see, clearly how our micrograph look like. Instead of just see the value statistics, I would check for each micrograph. So we can improve the validation like using the circular averaging approach, but there is some big problem about this approach because of the astigmatism. And when you average the high frequency information, it's always nothing, and completely average out the signal. And a better approach is called elliptical averaging. That means you somewhat consider about the astigmatism and average across this elliptic contour, and rather than a circular contour. But there is still some problems about the elliptical averaging. That's because of the CS. Because in the presence of the CS, the tone rings are not perfect elliptical. You can prove that mathematically. But I will just show you what's the ideal averaging approach. It's called the equal phase averaging. That means you average all the power spectrum by tracing exactly the same phases of the CTF curve. And then this is not elliptical, obviously. But in some special case, they might be equivalent, like without the astigmatism, the circular averaging, elliptical averaging, and equal phase averaging are all the same. And without the CS, elliptical averaging and the equal phase averaging is also the same. It's ideal elliptical. But I would suggest even better approach that considers the high noise of the micrograph, because the signal noise ratio in the Cryo-EM micrograph is very, very low. I mean, even the equal phase averaging sometimes fails and high noise micrograph. And by applying a maximum likelihood approach, we assume that there is some error or some estimation error. And we don't do a single, counter averaging, but allows a slightly wide range of averaging by some kind of weighting, assuming there is a distribution of the error like the Gaussian, and then you average all the power spectrum in this region. And then in some case, there are some parameters to control the averaging, like this constant. And if it's 0, it's just equal weights for all the information here. If it's infinitely big, it's just a delta function and reduced to the general equal phase averaging. And let's have a look how it helps our diagnosis. So here are two results. Our challenging faceplate data set, and deliberately choose the different parameters to let one estimation be successful and the other estimation is wrong. Can you guess which is correct and which is wrong? Probably not so easy, but I will tell you. The bottom one is the correct, and the above one, the results, is horrible. And you can see the estimation end up at around 9 angstrom resolution, and the other you see 12 mole tone rings, and you can't see this from the original power spectrum. And this doesn't mean that there's no signal. It's just the signal is so weak that you can't see it clearly by eye. After the maximum likelihood equal phase average, you see clearly the rings, and also you can judge which is correct, which is wrong. And there's another even more challenging case, and in this case, these two estimations are almost identical. There is only a slight error for one of them. Can you guess which one? Of course you can't, because they seem identical, and all the rings fit very well, but essentially the bottom. This one, you see a slight error here. From the beginning, you can't see anything. But in addition to the diagnosis, we can actually still apply it for better refinement. Because we see the difference, why not apply this difference to correct our estimation? That's my approach for further refinement after equal phase averaging. So first we did normal CTF estimation using GCTF, and then do maximum likelihood equal phase averaging, and then refine the average, the defocus, and phase shift using the average, the power spectrum, and then locally, and then we go back to the original power spectrum and refine it locally, and then do new equal phase averaging. And you can get the same results from this to this. But I will just show you one more example. And in this case, you can see the estimation is pretty good. You can see very high resolution information fit very well, but it's not perfect. We can still improve it a little bit by seeing the tone rings almost up to the Nyquist information. You can see the slight difference. And there are still some rooms for improvement. But that's not all. I would suggest even more powerful approach. That's called the generalized equal phase averaging approach. What does it mean? So no matter in the normal equal phase averaging or the maximum likelihood equal phase averaging, you're basically only averaging one power spectrum, or just a series of identical power spectrum with the same defocus and astigmatism. But actually, you can average different power spectrum using the equal phase averaging by release the frequency. And then you can average this, and this all together to get more information. How could it help? Or how can we, utilize this generalized equal phase averaging approach? Because it's just a concept for improve the signal noise ratio. It can potentially be applied to a number of different situations, and like movies, tilting micrographs, local particle CTF estimation, etc. But I will just show you one example about the tilting micrograph, a CTF estimation on the tilting micrograph, and you can see the power spectrum along the tilt axis is basically, quite similar. You can't see much difference, but perpendicular to this tilt axis, you see a huge, defocus variation. If you enlarge it, you can see that the phase shift. There are, a huge phase shift. Around the high frequency, and you completely lose your information if you use the average CTF information. So we use the generalized equal phase averaging approach to improve the CTF estimation of the tilted micrograph. How does it work? So we change the target function and add one more parameter, the unknown tilt axis and tilt angle. It's called T here. It's all together. And then maximize the cross correlation between the simulated and the generalized equal phase averaging. Based on the parameters. And I should mention that in this target function, we basically estimate the central defocus and the astigmatism and the central phase shift and the tilt axis and tilt angle. But it's still not localized CTF information. But we can simply apply this local CTF, get the local CTF information by applying a geometry offset. It's basically quite simple, applying a Z-shift. But this is not the ideal case. We can do it slightly better by the geometrically constrained local CTF refinement, or if you have reference, you can re-refine it using the reference for local CTF. You will benefit from the structure information as well, instead of just a power spectrum. And I will show you how it helps our estimation. So this is an average power spectrum of the tilted micrograph. And you can see very nice tolerance and the low frequency, but at the high frequency, it looks quite weird. And you can see that there is some missing rings here, and then you see these rings again. What does it mean? If you do the general maximum likelihood equal phase averaging, you see it's weird here. And actually, because beyond this frequency, the phases are already flipped. You have completely wrong structure information. You can't just correct your CTF using this CTF information. But if we do the generalized equal phase average, you can see a tone range all up to very high resolution and nicely fitted to all the theoretical tone ranges. And you see much better signal noise ratio. I will just show you one example. How can we improve the structure determination by tilting the stage? This is the approach that we can solve the orientation preference problem. That's one of the biggest problems in our CRY-EM structure study. And before and just using the global CTF, I got like 8 angstrom reconstruction using roughly 1,500 particles. And this resolution is well estimated by the 19-degree CTF phase error criteria. And then I focused on each particles, and then suddenly the map was improved from 8 angstrom resolution to 3.8, and we see clearly side chains and could build the model. And in addition to the CTF information from tilted micrograph, I would mention that we still have some information lost during the movie data collection, because each frame might be different. And if you average all the information together, just using the average of the frame, or you just average the Fourier coefficient of each frame, it's actually identical mathematically, and you get something like this. You just see a couple of rings. This is because of the drift, charging, radiation damage, and thermodynamics of the molecules, and and also particular beam-enhanced thermodynamics of the molecules. And if you do the averaging called the incoherent averaging, and you get a much better tolerance. This is already described several years ago by Greg and Richard. And you can see that you significantly improve the power spectrum. And this is because the incoherent averaging is drift independent, and no alignment is required. But I want to mention, this is not I want to talk about because people already described this. I want to talk something about the opposite side. That's the extremely low dose. So you can see that in the extremely low dose, the incoherent averaging, no longer works well. Why? And you see that it gradually loses more and more information. The problem is that the incoherent averaging completely get rid of the phases. And when you average the power spectrum, when the dose is extremely low, it will actually magnify the noise. Why? So we just think about one extreme case, that your detector is very, very fast. That allows you to detect a single electron for each frame. In total for a single frame, there is only one electron. And you do Fourier transform. It's a constant function. Is this correct? And then you average all the frames. It will still be a constant function. So when and considering it's a continuous function, when you get less and less and less dose, you will finally converge to a constant function, and the average is identical to the real space averaging, because the power in both real space and Fourier space must be the same. So that's the problem in practice. And actually, interestingly, in most our practical case, the dose is just in between these two factors. And on one side, you have the problem about the drift, beam-induced movement, charging, etc. But on the other hand, you have very low dose for each frame. And using the incoherent averaging, you lose signal. So the best strategy is trying to combine these two together, the incoherent averaging and coherent averaging. Usually, the aligned frames is better. And the ideal case is doing some kind of weighting schemes. But before we can do the weighting, optimize weighting schemes, we need to accurately estimate the CTF of each individual frames. And this is very challenging. You can see there is almost no signal. But actually, GCTF, I mean, the refinement approach in GCTF can still get quite a reasonable estimation of the frames. And this is the estimation. It's quite noisy, but you can see the trend is pretty good. And then maybe you can also do some similar approach like the smoothing, similar to the phase shift estimation to constrain the defocus changes along the z-axis. And then after you estimate the single frame CTF, you can do a better weighting, etc. But that's something we can discuss later. I just want to quickly mention something. I mean, we can do even better when we benefit from all the local CTF, frame CTF, and particle CTF, etc. We can combine all this information together to optimize our weighting functions, and you consider about the effect from the dose, from the drift, and also from the CTF quality. And these weightings are quite different. For the drift, the first few frames are usually quite severe, and the dose is, I mean, the first, for the dose, sorry, maybe, yeah, I should be quicker. And I just quickly show you how it looks like. And this is just 1 pixel, and you can see the different directions, the weighting is quite different, and it's also anisotropic in x-axis and y-axis, they are different. And then, I mean, by better weighting, we can get much pre-polished particles and get better results. And finally, I want to quickly mention something about the evil sphere correction. So we have a 3D structure, and the defocus varies. Even if it strictly obeys the weak phase approximation, you still have problems. And if you consider about the multiple scattering, things will become more complicated, and also the interfere between the transmission beams and scattering beams, and there are more problems. And the coefficients in the bank focal plane is not symmetric. And Hongzhou proposed such an analytical approach for the evil sphere correction, and I think there are still something we can do to slightly improve that by considering the signal noise ratio, because in this approach you will have the problem about the zero values of the denominator here. So we need to consider about that. And I want just to quickly mention some work from other groups. And this is recently, just several days ago, published a structure of held wires and 3.1 angstrom resolution. They used the focus compensation and local alignment approach to improve the reline structure to 3.1 using their own programs by correcting the UL sphere by the defocus compensation approach. And actually, this is already implemented in UHA's script for the local refinement 3 years ago in their script. They didn't describe that method previous, but it has been fully implemented in their script. And Hongzhou SLAM used that approach to solve a similar structure. And also, this guy described a number of different approaches for UL sphere correction in his thesis several years ago, but it's in Chinese, unfortunately. I wanted to describe a little bit about my approach, but maybe next time. I just quickly want to show something. I'm going to I'm mainly working on Dunning and dynamic system, and this involves in a number of cell activities and important diseases. And we are using CREM and ET approach to study this dynamic machinery, hopefully, and atomic resolution. And I'm going to move to Yale this October, and this will be my lab. And this is, but eventually it will look like this, a beautiful campus and postdocs available in Yale University. and want to thank all my lab members and collaborators. Thanks.
All right. Yeah, okay, thanks a lot. Okay, we have time maybe for some brief questions. I think you've stunned everyone. Oh yeah, okay.
Hi, I think I wasn't quite clear on something really right back at the beginning, that you were talking about systematic increase in error, defocus estimation over an experiment.
Yeah.
But that was, you only showed if you increase the defocus over an experiment, was that right? What if you don't increase the defocus, the error? The reported defocus would still...
You can't actually do that. That's because the defocus value from the experiment is severely inaccurate. You can't actually, perfect focus your target. It's very challenging.
I think I didn't understand that bit properly. Were you showing that the error in defocus reported from microscope over an experiment?
That means you do one exposure and this region, and it might not be 0. Let's assume it might be 1.5.
Yeah.
And then you adjust the offset to 1.505, and then 1.507, and then you compare, and then you assume that you estimate the original defocus using the program, and assume that's the experimental defocus. Because experimental, if you read it from the microscope, it's not more accurate than the calculated. And I bet it's not better than the count.
The defocus changes you apply. The real defocus changes.
Yes.
There's an error, and that increases as your defocus changes get larger, but also over the course of the experiment.
Yes.
What if you don't make your defocus changes any larger over the course of the experiment? Maybe the way the graph was laid out was confusing.
Just using the same.
Yes. Yeah.
That's still the problem I described. You can't get accurate defocus readout from the equipment. You never get the accurate value from the microscope itself. I don't mean never. It's very challenging. It's more challenging than computational approach.
Okay, I think probably we're running out of time here, so this was all very interesting. But is that specific to a particular microscope? That curve, that deviation, is that per microscope? If you did on different microscopes,
for micrograph,
you see a different.
Yes.
No, microscope.
One microscope. Yeah, for different microscopes, it will be different. Maybe if and actually we can adjust the microscope value using the re-estimated, using the computational approach to compensate the microscope.
On each microscope.
Error.
Okay.
It's the calibration.
Yeah, it's basically the calibration.
It's the basic calibration of the microscope.
That's true.
How much
That's
current you count for defocus.
Yes.
So it's a maximum.
Exactly. It's basically calibration. Yeah.
Okay, I guess we've gone a bit over time. So thank you very much. That was great. Yeah.